Good afternoon, everyone. I welcome all viewers to the PRL ka Amrut Vyakhyaan. Today we have the 20th Vyakhyaan, or the colloquium of the series of 75.
If you'll excuse me, I must get back to my painting. Do you care for painting, Miss Morton? I find it very soothing. Come see us again sometime.
I hear some sound from someone's microphone. Bushidji, can you please take care of that? Okay, thanks a lot. So I welcome all viewers to the PRL ka Amrut Vyakhyaan. Today we have the 20th Vyakhyaan, or the colloquium of the series of 75 Vyakhyaan that are being organized to celebrate the Platinum Jubilee of the foundation of the Physical Research Laboratory. This series of Vyakhyaan began on 4th of August this year and is held every Wednesday at 4 p.m. And the lectures are being delivered by eminent speakers from India as well as abroad, from very diverse fields, including science, engineering, arts, and literature. Today, we are honored that we have a very distinguished speaker for the Amrut Vyakhyaan, Professor Sreerup Raychaudhuri, who is a renowned high-energy physicist and is currently working as professor at the Department of Theoretical Physics of the Tata Institute of Fundamental Research, Mumbai. On behalf of the director, PRL, my colleagues, and also on behalf of the Amrut Vyakhyaan Committee of PRL, I extend a very warm welcome to Professor Raychaudhuri and thank him for gracing our celebrations of PRL at 75. I would now request Dr. Navinder Singh to introduce the speaker to the audience and to invite him to deliver today's Vyakhyaan. Over to you, Navinder.
Thank you, Prasananta. It's a pleasure and honor to introduce Professor Sreerup Raychaudhuri to this audience. He is a theoretical physicist par excellence and an eminent scholar who has contributed not only in the particle physics but also in the history of science in India. Professor Raychaudhuri, through his very popular book, Particle Physics of Brain Worlds and Extra Dimensions, contributed significantly to the pedagogical presentation of this very difficult and challenging field. He is an excellent speaker and a great teacher. From this book, many newcomers into the field have benefited greatly. So today he is going to speak on collider physics, but he is also his other interest on the history of science in Indian context is also very welcomed and very much praised. So maybe at some other occasion we will have him here on this Vyakhyaan or other platform, and we'll have the pleasure to listen to him on that topic also. Okay, with these words, I invite Professor Raychaudhuri for today's Amrut Vyakhyaan. Professor Raychaudhuri, I am giving to you. Professor Raychaudhuri,
you need to unmute yourself.
Yeah. Yes. Thank you, Navinder, and thank you, Nandita, for that very warm welcome. And very. I'm just trying to. Okay. Then I'll just try to share my file first. So. Share file. Where does it take me? This is looking a little different from when we tried it. So this must be the one. Is it visible?
Yes, we are able to see. Yeah.
Maybe I'll make it full screen now.
Yeah, full screen.
Yeah, is it visible full screen?
Yes.
Yes.
Okay, fine. Then I'll start my talk. But before that, I'd really like to thank you, not just for the welcome, but for inviting me to give a talk in this distinguished series. And while I will just talk, so I will talk about future colliders. Well, it's not moving. I'll talk about future colliders. And during the course of this talk, I will talk about some things about how particle physics is going nowadays, how the present and then possibly the future. Sort of it will be a mix of various things and some analogies from the past. As you heard, I am interested in history, so some of those things will also perhaps show up. And then, of course, we will, so it will be a sort of mixture of the present, past, and future, and I hope you will enjoy it. So today we have a large collider called the LHC.
Yeah,
And
Raychaudhuri, we are not able to see your slides.
Yes, it is not changing actually.
I think there is
We are only able to see the first one.
Yes.
I see. Okay. So
maybe you unshare and then
Again share.
and then go to the full screen afterwards.
yes, the point is that I have a problem. Just a minute. See, I have a problem that now when I click share, I get something called shared file. Earlier, I was getting a picture of my desktop. So I'm not quite sure how to handle this.
Yes, now we see standard.
Yes, standard model, modern colliders.
Okay. Let me go back. Then we'll see if it. I can't go back on this, but I can go forward. All right. I can go forward. So is the new slide visible?
Yes, with the cartoons.
Yeah. Just 1 minute. Let me just stop the video for a moment. I'll see if I can do something better. I'm sort of. How does one unshare?
I think that's a good idea.
Yeah. Yes, good idea.
How does one unshare? I'm not getting the unshare prompt at all. Okay, maybe what I'll do is I'll just. Oh, I see. There must be something. I must have been logged out and logged. I'll leave the meeting and come back. It's probably the best thing to do.
Okay. We are still seeing his slides, even though he has left. Bushiji, can you remove this?
I am trying that.
Okay.
I could see a picture of the whole screen. I'm not. When I click share, instead I'm just getting something called shared file. Instead of getting a picture of the desktop, which I then clicked. Is there a technical problem here?
You have to open the file, open the presentation, and then share.
Now I've got it. I think I was not the presenter or something like that. Okay. Now is it visible?
Yes. We see the first slide
Okay.
as
Yes. Okay. Good. Yeah, it's correct.
Has it gone full screen?
Yes,
Yes.
full screen.
Okay. Then I think we are in business. All right. So this is my first slide, and as I said, I will be talking about future colliders. Is it working now?
Yes, perfectly.
Okay. Thanks. So what I wanted to say that we have a collider today called the Large Hadron Collider, or the LHC. And this has been running for about 10 years. But as it has been running, what we have discovered is that this has really become the standard model collider. The results which we have got from this are completely consistent with the standard model and not with physics beyond the standard model, which has been sort of the holy grail of today's particle physics. So then we come to the other. So, okay. So here is a picture of what we had earlier, of what we have from here. This line is basically the standard model. So it's a sort of data by theory, where the theory is the standard model. And you see everything clicks to one, everything is very close to one. The data, so we have, of course, there are things where the errors are large, difficult to measure. But whatever measurements we have, everything was very close to the standard model. People have also looked for physics beyond the standard model, extra dimension, which is something I've worked on. Gauge bosons, dark matter, heavy quarks, lots of things. All we have are exclusion bounds. So they're exclusion bounds. And then even the standard model Higgs. So this straight line is where it's a graph between the coupling strength and the particle mass. And all the different particles across this huge spectrum of masses, you can see so many orders of magnitude. Everything matches so beautifully with the standard model. If you look at this graph, this is the ratio of the results. Again, it's so close. So certainly at this point, it is clear that in the competition, the standard model is winning, and the beyond standard model ideas have all taken a big knocking. So that's where we are today. So this standard model, of course, has been described as the unsung triumph for modern physics. And this is a picture of the particle spectrum. So all the particles in the standard model stand up today like, a great wall which you cannot breach. Now, I'd like to point out that much of this triumph has been achieved because of the high accuracy measurements at colliders, at colliding beam machines over the years. The ones which I marked in red here have all been discovered at colliders. So as you see, much of the standard model has been built up by colliders. I'll sort of do a recapitulation of that. So the first one, the partons, which are the quarks and the gluons, they were the light quarks and the gluons, were discovered at SLAC, the Stanford Linear Accelerator Center, and SLAC is the collider they had between 1969 to 73. And here is a graph which sort of shows you that indeed these exist. Then the charmed quark and the tau lepton were discovered.
Sorry to interrupt you. I am very sorry to interrupt you. So there is a on the top of the screen, viewing Sreerup Raychaudhuri's application. I think this watermark or something like. So if we can remove, then the first line can be read.
Has it gone?
No, it is there actually.
Well, it's not on my. This is all WebEx. There's nothing which I have put there.
Okay, it is coming from the WebEx. I see. Bushit,
Yes.
is it possible to, because it is covering the first line of the all slides it will cover?
Yeah, I can see that. But is there any solution to this?
No, right now I don't see any option to remove it.
Can it be moved away?
No, that is not movable even.
Yeah, is there an option to remove it?
It's not coming in all the presentations. I think you have to move out your mouse, Navinder, and put it out. Then it will not come. Okay, it's a issue the way you are viewing it.
Okay. Maybe. Yeah.
Has it gone, Navinder?
It is not visible in YouTube. It is not visible in YouTube.
Okay, please go ahead. No problem. Please go ahead. I will rectify on my end.
Okay. So I've talked about the charmed quark and the tau lepton. You see these are the original graphs in the papers where they were discovered. You see these little peaks. Of course, these discoveries have been much better established now, but these were the discovery graphs. Then the famous discovery of gluons at the Petra collider at Daisy. And this is the picture of the triple jet events which happened, which prove the existence of gluons. Then the W and Z bosons, as we know famously, were discovered at the CERN's SPP-Barres collider in 1981. UA1 is the name of the collaboration. So this is the big one which came in the end of 1982 and in early 1983. This was the Z boson. So this little peak was the Z boson. So they were discovered there. Then the standard model was tested to the quantum level by the LEP collider between 1991 to 2001. And the LEP collider, these are some of the results which are really at the loop level, at the higher orders in quantum theory level. And this is what we get from them. Moreover, the electroweak unification was beautifully tested at Hera. Pure weak force interactions and the electromagnetic force, the corresponding interaction cross sections, they came and met at this point, which is really the electroweak cross section. So beautiful proof of electroweak unification was again achieved by the colliders. The top quark was again found at the Tevatron, which is another collider at Fermilab in 1994. And of course, as everyone knows, the Higgs boson was found in the LHC. Here is a picture of the picture they had in the beginning to show that the Higgs boson has been found. This blue peak is the Higgs, and it was found at the LHC in 2012. So here is the list, the Bartons, the slacks, Chauvet ones, and so on. So the triumph of the standard model is as much a triumph of collider experiments as it is of quantum field theory and the gauge principle. So this is my first thing, and therefore colliders are good. That's the point I want to make. Now let's come and talk a little about the standard model as a theory. And I'm likening the standard model here, the basic ingredient, which is a local gauge field theory based on the group SU2 cross U1. The details are not needed for those who are not in the subject, but it's a group based on a group theory. It's a very beautiful theory. So I liken it to a beautiful animal like this antelope. But however, if this had been the only theory, then we would have loved the standard model as a theory. The trouble is that this theory alone doesn't work. And what we need is to be able to break this theory and make it ugly by putting in a scalar field by hand. And this ad hoc introduction of a scalar field, which breaks the electroweak symmetry, it sort of creates a very strange nature. But this is not the end of the story. There is more. We have to put in parity violation by hand. So basically, we are taking another bit off the animal. We have to put in CP violation by hand. That sort of breaks its horn. And finally, at the end of it, the standard model has no place for neutrino masses. The fact that we have neutrino masses also takes away an eye. And now this sorry-looking creature is what we call the standard model. So if you went into a forest and you found an animal like this hopping around, you would surely say, poor fellow has been in an accident, and actual theory, the actual animals, we should look for other animals in the forest which are whole and which are much better. So that is the situation of particle physics. We have a theory today which is fine, it's alive and well, but it's a sort of incomplete theory and an ugly theory at the same time. So there are 7 great questions which we can ask and which the standard model doesn't do well on. So the first 2 are ones in which the standard model is completely clueless. These are the ones when you address the universe or the cosmos as a whole. We have evidence for dark matter, we have evidence for dark energy, which causes the universe to accelerate. The standard model is utterly clueless about these. There is nothing in the standard model which can be interpreted as dark matter or even less as dark energy. Then there are the unexpected things. So one problem is that of baryogenesis, which is that the baryons or the normal matter in the universe is much higher than we would have expected. Because we expect that after the Big Bang, the universe would be mostly radiation. And then the radiation, you would pair create a lot of matter, and the matter would come. But of course, when you pair create, you create as much antimatter as you create matter. So there should be lots of antimatter around. And it turns out that the antimatter is not there. So we have lots of matter, but not enough antimatter. So where did all the antimatter go? And that's something which is not answered in the standard model. And then, of course, there's the neutrino mass. Standard model was beautifully constructed around having neutrino mass is 0. And if the neutrino mass is not 0, then why is the standard model what it is? Why is, in fact, if the neutrino mass is 0, why is it so close to 0? These are questions which the standard model cannot answer. And finally, there are the issues which are sort of embarrassing. I mean, they are not things where there is no answer. So there is, first of all, the strong CP problem. Why don't we have CP violation in the strong inly interacting sector? And we answer that simply by putting a parameter to 0 by hand. Now, one of the lessons of quantum field theory is that nothing becomes 0 or very large on its own. There has to be some better reason. The second question is about stability of the electroweak vacuum. The electric vacuum, it looks like it's just on the cusp, according to our measurements, of between stability and instability. So if it is unstable, then of course there will become a position time when the whole universe is going to collapse in a sort of fireball. But if it's stable, it remains stable. We seem to be just on the border of that. So how come we are so close to the border of that, and is it really stable or not? And last but not least is the hierarchy problem. So I'll explain the hierarchy problem to you. The Higgs mass should really be at the Planck mass. So in fact, but it isn't. The mass, this is the mass of in GeV, and the mass is just the difference of these two. So 1.2 in this unit, and we have this massive cancellation of so many digits. How can such a cancellation happen on its own unless there's a reason for it? The standard model gives no reason. It just assumes the cancellation occurs. And of course, the biggest puzzle of all this is, why is a makeshift theory with 5 different kinds of things thrown together, why is it so successful? If you make a makeshift theory, then it should break down at various places. It's not breaking down. So what is going on? So there are 5 possible explanations at the moment, why we have failed to find evidence of physics beyond the standard model. And I will sort of now take you one by one through these 5 possible explanations. The first one is, of course, what I call the philosopher's stone explanation. Now, you may have heard of the philosopher's stone. You know, the alchemists believed that there would be something called the philosopher's stone, which would be such that when you turned it, when you touched it to an ordinary metal like iron or copper, it would turn into gold. They spent centuries seeking it, and of course they didn't find it because there is no such thing. Such a thing doesn't happen. There is no mechanism to turn iron or copper into gold, and that's why they didn't find the philosopher's stone. So is it the same for the new physics? Is the standard model final theory? Then all searches for anything beyond it are doomed to fail because there is nothing. So this is one way of looking at it. But then, of course, we have to answer the question that how come such a poor theory, a theory which is sort of, like 4 different theories which you put together, how come this is the final theory? Is nature so poor imagination? So that's the first possible solution. This is the sort of zeroth or the trivial solution. Other possibility, of course, is that there are many universes, and all sorts of possibilities are there with CP violation, without CP violation. We just happen to be living in one of them, and that's why we see only this. In other universes, things are different. But that really is telling us that there's no point in doing more science because things are as they are, and then you stop there. Well, there is the Galileo's lantern explanation. So let me tell you about Galileo's lantern. So Galileo was the first to try to find out how fast light travels. So he went and stood on one hill, and he sent his assistant to another hill, and he said, okay, I'll uncover my lantern, and as soon as you see the light, you uncover yours. And I'll take the difference. I'll measure the difference with the pendulum clock which he had invented. And see, but what Galileo found was that this was instantaneous. Okay, that he couldn't measure any time in between. So of course we know the reason. Light travels much too fast to be measured by a system like that. The time involved here is much smaller than even the reaction time of the assistant or of Galileo himself. So this failed simply because it was trying to do something which was not that it was not there. Light has a finite speed, but the speed was just beyond the capacity of the measuring machine. So that argument would be that there is BSM physics, beyond standard model physics, but it exists at a higher energy scale than what we can achieve or what we are planning to achieve. So the LHC, for example, will not be able to find it because it's there at a higher energy scale. We have not reached there. Just like Galileo was not have the ability to measure such small times. So then the question arises, can we devise a wholly new kind of experiment which would overcome this deficiency? Remember that for the speed of light, Fizeau and Foucault, both of them had two different experiments which you could do in the lab, and you could measure the speed of light. So can we think of something which would discover these without really requiring a very much great improvement in energy? So do we have a probe of much higher energy scales? I'll come to that. Then there is the malaria explanation. What is that? For many centuries, people thought that malaria was due to bad smells. The very name malaria comes from mal, which means bad, and air, of course, is air. So bad air. And actually, people went around smelling perfumes and covering their noses, hoping that it would save them from malaria. I mean, even today we have seen people doing all sorts of strange things, hoping it will save them from COVID. But it was not until Ronald Ross found the mosquito was the culprit in 1897, that people found how to avoid malaria. So is it possible that we have been looking in the wrong direction? There is new physics beyond the standard model, it's observable, but we have not been looking for the signals. So the signals were there, like mosquitoes were already always there, but people ignored them. So is it possible that we have simply ignored those signals and they are lying there just waiting for us to look at them, just like Ronald Ross? The mosquitoes were there. So when he looked at them, he found the solution. Now, this means that the question is, can we search in some unbiased way? Because most of the searches are for signals which somebody has told you is there. Is there an unbiased way which will catch the signals, whatever they are? That's the way to think about it. Then there is the gravitational waves explanation. So this is the point, that gravitational waves exist and people had been looking for them. It's somewhat similar to the Galileo thing. But only the people also had the right technique. Galileo's technique was not the right technique, nowhere near the ground. But the techniques were also right, but they failed because gravity is just too weak. Only because we had vastly improved technology, and we were fortunate that a truly catastrophic cosmic event gave us strong enough gravity waves, and that is when we were able to find it. So what is perhaps happening is that there are new BSM physics and the signals have been there all along. But these are very small signals. They're getting lost among all the stronger standard model backgrounds. It's getting lost in the noise due to standard model. So can we enhance the signal to background ratio in any way? Which is what LIGO did, reduce the noise and find the very fine signal. Is there some way we can do that? It's easier said than done. Then the last one, of course, is the Uranus explanation. What is that? The planet Uranus was discovered in 1781 by Herschel, who saw this through his big telescope. This, of course, is from a better telescope than Herschel's. But it was then discovered that people had seen Uranus before. They had plotted it as a star on star charts. It had been 6 times before. Uranus had been seen and plotted. But they didn't have big enough telescopes to see the disk. But if they had plotted to check after some time whether that star had moved or not, they would have found a planet. But no one had checked to see if anything had moved. And as a result, the star plotting had been there and people had failed to discover Uranus. It was only discovered by Herschel. So it could be possible that there is beyond standard model physics in the existing data. But in our haste to look for familiar things like supersymmetry, extra dimensions, technicolor, all these little Higgs, all these standard things, we have overlooked it or we have misinterpreted it. We have just simply misinterpreted it as noise or something else, and the signal has been sitting there all along. So then it's worth taking again a hard look at the existing data with some kind of unbiased analysis method. And I'll come back to this. Now, how can colliders help in this? So these are mostly methodology, but what can colliders do to help us? So let's first look at the philosopher's stone case. So if the standard model is the only one, then we should be able to understand it. And for that, we need to measure its parameters very precisely at different energy scales. Different energy scales, the running of coupling constants, running of masses, tells us something about the underlying field theory. So if it's the only theory, we will have to understand it and try to discover connections or correlations which tell us why all these parameters have these values. So to do that, we have to notice that of the 24 standard model parameters, the only ones not yet measured are the quartic scalar coupling and all the neutrino masses, the exact neutrino masses, and the phase of the PMNS, that's the neutrino mixing matrix. So more precise measurements may reveal unexpected features. So basically, we go on doing what we do, like this person who is running, though very tired, will still continue to run. And as we go ahead, we will find better measurements. And colliders are actually most useful in measuring this lambda, this quartic scalar coupling. And the others are better measured from non-collider experiments. However, measurements of all the parameters at higher scales, as I said, will test the standard model to loop level, and perhaps the running will give a clue to their pattern and to a deeper understanding of why the standard model is the way it is. So this is the case. This we will probably do this anyway, but this is the only thing we will have to do. If in the philosopher's stone case that there is no BSM physics, no beyond standard model physics, is the solution. What if there is the Galileo lantern case? The new physics lies at much higher scales. The point is that thanks to quantum mechanics and quantum field theory, this higher levels physics is going to manifest as tiny deviations at the quantum level from the standard model predictions, and perhaps some rare processes which are beyond standard model, and only much more precise measurements and very delicate searches can unveil these. So it's like looking at things carefully under a magnifying glass, and this job can be done effectively only at colliders. Of course, partially at other non-collider experiments also, but colliders are our best instrument to do this. Now, what we do is that we can, and we do this, we write down effective field theories using only symmetry arguments, and then try to predict beyond standard effects using the higher dimensional operators. This is a big game which people are playing around, but this is easier said than done. And eventually you end up with a lot of BSM assumptions in it. And if we do find, the parameters one measures in these theories are called Wilson coefficients. So if we do find these non-zero Wilson coefficients, we'll have to look for correlations between them and then try to guess the underlying fields. So that's one way. So, more precision measurements is one way to go. Then there is the malaria or Uranus case. They're very similar. That have we looked in the wrong place, or have we looked in the right place and not looked hard enough? So we will perhaps have to combine better technology, and hopefully we will, with the help of serendipity, we will be able to discover the signals. So what we need to do is to pick up more signals, and we need to go to higher energies and luminosities. This is like in the early days when there was a fort which you could not break. People took this battering ram and kept on hitting at the fort. They kept on hitting at the wall, still the wall broke in some place. So maybe that is job will be left to colliders to do. So we can build two kinds of machines. We can build discovery machines, which are hadron colliders like the LHC, and also precision machines, which are lepton colliders like the LEP, and keep on looking. So if we do find that there is BSM physics at higher energies, we may then be able to extrapolate to current energies. Eventually, if we do find, extrapolate to the current energies to see what we have missed. I mean, like the malaria or you read stories, we then exfoliated and became wise after the event, but admittedly that's an academic exercise. But this effort may throw up the needle. So if you're lucky, then DSM physics may be just around the corner, but perhaps not in any one of the forms we have been expecting. So we need to go on running the LHC and to build precision machines at the same energy ballpark, and only if enough energy accumulates can we at all think of filtering it for these very rare events like the gravitational waves. And also theorists, they need to devise more unbiased search techniques which would throw up new effects with as small a data sample as possible. And now, in fact, a lot of that is being done by using ideas which come from computer science, machine learning, artificial intelligence, ways by which the machine could help us to have an unbiased search techniques. It's still in its infancy, but perhaps one day we will do better. So then, of course, if we do find BSM signals, we find that they are really there at the LHC, then we will know what they are. Once we know what they are, the next generation of colliders would be built to probe this new physics. So having said all this in favor of having more colliders, let me say something about the kind of new colliders which are being contemplated. So let me start by saying that, if you want to make a collider, you have to accelerate particles. So they have to be charged particles so that you can accelerate them to high energies. And charged particles have to be stable. So the only ones which are readily available are the electron and the positron, the proton and the antiproton, and to some extent the muon and anti-muon, because muons have a large lifetime. And if you accelerate them to high energies, that means high velocities, the lifetime will get time dilated and will become, for all practical purposes, stable. So these are the only ones with which you actually have people have been thinking of colliders. Now, if you collide electrons and positrons, or you collide muons, then you call it a lepton collider. If you collide protons with protons or protons with antiprotons, we call it a Hadron collider. So, of course, the one which immediately will come up, which is the high energy LHC. The LHC itself will go on to higher luminosity, but the LHC is a Hadron collider. So that's the first one which will come up. Then there is the Chinese suggestion of the SPPC. And finally, at CERN itself, they are thinking of the FCC, or Future Circular Collider, which could run in both hadronic or electron or hadron-electron mixed mode. That's the possibility. That's also been approved, so I'll come to that. And in lepton colliders, the International Linear Collider, which will be an E plus E minus collider, is the first one on their bill. The Chinese have proposed something called the Chinese Electron Positron Collider. And then a CLIC is an electron positron collider which CERN have come up with. So this the European side has come up with this. So this is not European. ILC will come up in Japan. Then there is the possibility of a muon collider. So that's been very seriously thought of. Muon anti-muon collider. And one idea which keeps coming up is to have a photon-photon collider where you shine a photon on an electron or proton beam, and the laser photons backscatter with much more energy, and then you can make them collide. So we don't have a definite proposal yet, but the idea keeps coming up because it's very clean in many ways. And it will also, of course, reproduce what happened in the early universe, where radiation annihilated to give matter. And finally, there are ideas using laser plasma fields, which I will come to at the end of our talk. It's a very promising line of research. And perhaps if I gave this talk, let us say 30 years down the line, assuming I would be alive at that time, and perhaps all my talk would entirely be about laser plasma colliders. Perhaps. We'll come to that. So what are the differences and advantages between these kinds of colliders? So what happens here? The leptons in circular storage rings, they go round and round the ring. They have an enormous energy loss from synchrotron radiation. That's an exercise in electrodynamics. So basically, you can't use them. After some time, you lose more energy than you pump in. So you have to use LINACs, or linear accelerators. So linear accelerators, of course, they also emit Bremsstrahlung, but Bremsstrahlung or Raman radiation is much less than the synchrotron radiation. So the result is that you don't lose so much, and the loss is controllable. So you can actually, but you have to be linear. The problem with the linear collider is that the longer you make it, then you have to make the collider grows longer and longer. Now, on the other hand, of course, protons or antiprotons are easy to hold in these because the low energy loss from radiation, I should say synchrotron radiation, goes as 1 by m to the 4, where m is the mass of the particle. So compared to the electron, for example, the proton mass, as we know, is 1836 times that. So to the 4th power, that basically means that the synchrotron radiation can be ignored. So as I said here, ramping up energy requires a very long machine. And what happens in energy, you put little accelerating pieces. So it gets accelerated in stages. So you'll have to keep putting more and more of those pieces, and it will become a very long machine if it's a lepton collider. On the other hand, here you'll have to put these RF cavities, which are the accelerating thing. But the ramping up energies is possible. You could put more into more density. Of course, there'll be an upper limit, but you could put more and more. Then there is another problem here, which is another advantage of the Hadron Collider, is that if you have a bunch of particles coming and they go around, so every time they go around, they cross each other. So if two bunches, let us say, go around 100 times, then they will cross each other 100 times, actually 200 times, because they'll cross 2 times when going around. Whereas if it's a linear collider, then each bunch you shoot them at each other, they cross once and then they go away. So getting a high luminosity or a high flux is the quantum mechanics term, luminosity is what particle physicists use. So getting a high flux is a challenge at lepton colliders. It's much easier at hadron colliders. And again, on the other hand, you can focus the bunches of the protons, electrons, you can bunch them into very intense bunches using high density bunches, using magnetic fields because of the large E by M ratio of these. So E by M ratio marks the sensitivity to magnetic fields, and that is possible with leptons. Protons, on the other hand, the E by M ratio is small. So focusing protons is a big problem. You require really, really strong magnetic fields. And in fact, at the LHC, for example, you need all these very strong superconducting magnets, which is why you have this huge, you saw in the first picture, this huge tube. It's mostly full of liquid helium. And you don't need all that for lepton colliders. And fairly strong electromagnets will do the job. A little more about this. So what about the physics part of it? That's the accelerator theory. So of course, at lepton colliders, leptons do not have strong interactions. So only electroweak cross sections, electromagnetic and weak cross sections are available. But hadron colliders can produce particles through strong interactions, so you can have huge cross sections. However, and then again, a wide variety of processes can occur because hadrons are not single particles, they are composites of various things. So both charge current and neutral current, all kinds of processes can occur. Whereas in lepton collider, the charge conservation will restrict your final states. So till now, you see the hadron collider seems to be obviously the better one. And then you have a fixed, but the advantage of this is there's a fixed center of mass energy. And here then you have the hadrons have their own pieces, so only 2 pieces interact, which means that they have intermediate center of mass energy, all kinds of things happen. Actually, you don't get most of the energy. A lot of it is wasted. And the important thing is that the lepton collider gives you a relatively clean environment. There's much less junk or noise or other particles around, whereas hadron colliders will have lots of junk, lots of other interactions with other processes occurring around. So to pick the signal is very noisy. So the Hadron Collider basically acts like a discovery machine. You look around and you find out, and you want to find something, like when you use a binocular, it gives you a lot of information, but it doesn't give you details. So this one is like a magnifying glass or a microscope, if you like. It gives you the details. It doesn't have such a wide field. You see only a small field, but that field you can find out all the details. So these are the 2 kinds of purposes, and obviously, as you see, they complement each other. Now, once that happens, so you're familiar with the Olympics. These are the motto of the Olympics is faster, higher, stronger. So that is what is aimed for by the Olympic athletes, and is generally the motto of it. Now, for colliders, there's a very similar thing. I'm just changing the words. So this is a picture of the lab. And so you want higher luminosity, more energy, and more precision. These are the things we look for. So given this, I'm now going to talk about various colliders and what we are planning to see in the future. And I've sort of exhausted a lot of my time, so I will sort of go through this fast. This is the plan for the LHC for the next few years. It will go to the high luminosity. HL stands for high luminosity. And the plan is that we are sort of here. This is the plan now. The run 1, 2 have been over, and it has waited for run 3. It got delayed because of the pandemic. But now in run 3, it will happen. And as you see that run 1 and run 2 have collected about 150 femto1 inverse, which is the measure of the flux or the luminosity. But run 3, it will go to 300, run 4 will go to 1000, and run 5 eventually, which will be about 2035, should collect 3000 femto1 inverse or 3 autobahn inverse at 14 kV. So lot more of data. Now what do we do with that data? So okay, here's a graph of how the thing should go, and we are here. Now what happens if you have this data? I'm just showing an example of a very simple thing. This is a double slit. And when you look at the double slit, let us say this is a random case, random with 100 particles, 100 electrons thrown through a double slit. Do you see any pattern? No, right? There's hardly any pattern. Well, this is with 1,000 electrons, and now you begin to see a pattern. There is a little bit of a pattern when you have thrown more electrons at it. What is the pattern? That you see more in the center and there are less towards the edge. So there is sort of clustering in the middle. Now with 5,000, you now begin to discern this clear pattern. This is your double-slit pattern. You begin to see the fringes. So with anything which obeys the laws of quantum mechanics, increasing the luminosity or increasing the flux, as you go to higher and higher luminosity of flux, you will begin to see patterns which were not there before. The patterns emerge. And that is the hope, that in the higher luminosity LHC, you will begin to see new patterns emerging. So there is still plenty of scope for unknown physics or unknown phenomena to appear at the high luminosity LHC, in which case we will have a rematch between standard model and beyond standard model, and who knows, this time it's the other guy who will have his hand raised by the referee. So for precision measuring of Higgs parameters, unfortunately, there is not much hope with the high luminosity LHC. It's part of the way the structure goes. I can explain the detail to anybody. However, the Higgs self-coupling is vital for the future of the universe. Why am I saying that? Because the Higgs coupling, self-coupling, needs to be known precisely to know whether the electroweak vacuum is stable or unstable. So if the Higgs self-coupling comes out as a value that shows that it will become unstable at some stage, then we know that the universe is going to end up in a big fireball. And if not, fine, it goes on expanding little bit by bit. Eventually, everything will expand away. You will not be able to see anything except ourselves, our own galaxy. Okay, then of course, there's a probe of how much supersymmetry could be seen. So here are some of the standard processes by which one looks for supersymmetry. This is what was seen in the first run, the gray things. This is how much improvement you would have at the 300 femto1, which would be the next run. And eventually this is how much. So you see the improvement will not be so much, but you would be able to see these processes which you're looking for. You would be able to push the weakly interacting, electroweak interaction super partners. You would be able to see them up to about 1 TeV, not even 1 TeV. But the strongly interacting ones, the limits would go well above 2 TeV. So the increase in the discovery rate is somewhat moderate, not very strong. And here are the various other kinds of things we could look at. As you see, the advantage of going to this 3000 femto1 inverse is limited. The machine will still do it because it's worth doing it. You already have a running machine and it's not worth stopping it. But the gains we will get are a bit limited. And then this thing is rather technical, I'll drop it. But it's much easier. A lot of increase in luminosity, the equivalent of that can be got by just a little bit of increase in energy. So I'll skip the details of this slide. So let me now talk about the high energy LHC or the very large LHC, Very Large Hadron Collider. Now the new name on the anvil is the Future Circular Collider, Hadron. So this, so LEP or the LHC has this white tunnel. So you see this picture, it's an aerial picture. This is Lake Geneva, this black thing here. This is the city of Geneva you see around here, and at its edge, as you know, is the LEP or LEP collider. So a new tunnel will have to, this tunnel will not do anymore. A new tunnel will have to be made, and this is the plan how it will go. And there will be all these stations around. You can't be too close to the tunnel. So that's how it's going to come up. And here are some of the parameters one is thinking of. There'll be a 100 energy will be 100 TeV center of mass energy. These luminosity will also be very high. Compared to the LHC, it will be some 5 to 25 times higher. The details one can forget. And the luminosity will be 2,500 femtobarns in the inverse in the first year. So there should be an inverse here. I forgot to write that. And in run 2, it will be 15 autobarn inverse, so 15,000, and run will be 40,000. So much more data collected, and of course at a much higher energy. So there is a whole study, detailed study on this called Physics and the FCCHH, 100 TeV PP collider. It's one of these CERN yellow reports where many people have contributed, and one needs to look at that. They've studied a variety of kinds of physics you could do there. But all the analysis is made under the following assumptions. First of all, the signal and background scale in the same way. The reconstruction efficiencies, the background rejection, etc. remain the same. The cross sections remain proportional to the parton luminosity. All of these may change. So there are various caveats. We do not know if there is any new physics thresholds between 100 TeV and 13 TeV or 14 TeV at which LHC will run. If there is, lots of new things will happen. All standard models will appear massless at 100 TeV. If all standard models appear massless, and the W, Z, A, stop, all these heavy particles at LHC, they will simply appear as jets. So it's a new way of looking at things. And of course, we do not know how the parton luminosity scales. We could perhaps get some information from high energy cosmic rays. That's being attempted now, but the cosmic ray flux is very low, so there's a lot of errors on those. Because remember, the parton luminosity, the parton density has to be scaled up from about from whatever energy we have now, 13 TeV to 100 TeV, and it could change dramatically. So here's a sort of picture of the kind of cross sections you get from there. You will see something interesting, that the BB bar cross section is very high at that stage, more than anything else beyond the total. But these are details which only a particle physicist would perhaps be interested in. So I'll skip that, and we can get better exclusion bounds and so on. I'll move on, I think. So here is the news item. So it came in 2019. CERN lays out plans for a 21 billion euro super collider. The price has gone up, of course, since then. But it was agreed that it will happen. The idea is that it will come in 2040 to 50. So this is still on the anvil, and this is still being considered much more seriously. The designs work is being done, R&D to start it. So perhaps those who younger members of the audience who will be active in 2040-50 will certainly see this machine. Now, the International Linear Collider, the idea of a linear collider was to follow up on discoveries made at the LHC. Now, those discoveries have not happened. But, it would be the same way as the W and Z were discovered by the Hadron machine, SPP bar S, and then the properties were measured at LEP. But we have not discovered those. So now the LHC program is a bit in jeopardy because Higgs is the only discovery. So now the proposal is to go ahead and build it anyway, so that either you look at it randomly to see what it does, or to measure the Higgs properties. And the physics case must be strong enough. So, but here is an example of what happens with luminosity. So precision matters. You see, these are the three experiments, or the three satellites which measure the cosmic microwave background radiation. So this was Kobe in 1992, which saw small fluctuations. This was the W map, which saw them much more precisely. This was the Planck in 2013, which saw them. So now we know much more, and therefore we understand much more about the early universe. So the precision matters, and this is what we will be getting from the ILC. And here is the sort of cartoon of what the ILC could look like. As you see, it's linear, it's very long, and that's where the collider is. Of course, you won't waste your electrons and protons, you'll send them back. So you could also make it in a more compact way, so that possibility is also there. And the energy can be ramped up simply by making it longer and longer and putting in more and more accelerating cavities. The only radiation which comes, as I said, is Bremsstrahlung, will not spread out. So for a circular collider, the radiation comes out tangentially, so in all directions. That means that you need to put it deep underground so that people are not affected by that radiation. But if it is only a forward peak, then you only have to see that in one direction there are no houses and people there. So you can build it on the surface. Or you can build it between two mountains, for example. So the radiation will be shielded by the mountains. And of course, the disadvantage, I've already said this, bunches cross only once. So you have to make the bunches very small and dense. And very small and dense bunches also tend to destabilize. First is because the internal fields are very intense. You have so many charged particles so close to each other. The beam itself, when two bunches cross or come close to each other, the electric field of one bunch, which is very strong, affects the other one. So I'll show you quickly a simulation of what happens when two such bunches come together. And you see that they've become a mess. They had a particular shape before they came. You look at the green and the red and the blue ones, and it has become a mess. So this danger is there. So the bunch quality deteriorates. So there'll be a spread of center of mass energies and so on due to these effects, but let me not go into the details. You could measure Higgs couplings with much better precision at this than the LHC. And you would be able to, could perhaps see new physics there. This is too technical, I'll leave it. And of course, you can also look for supergravity or supersymmetry at these machines. So the LHC has come up to here. You could, where the high LHC would be there, you would see somewhere in between. So here is a sort of cartoon of what the LHC could look like. This is planned for Japan, where it runs from between two hills, actually. That's what the suggestion I gave. And it would be on the surface. This would be the beam pipe. There would be a sort of platform. So it looks a little like the bullet train, and Japanese have probably planned it in that way. They use the same technology to build the tunnel. So Japan is now going forward to plans to expanding this thing. And the important thing is the Science Council has cleared it. It had earlier not allowed it, but now they want a participation from other countries also. So nobody has yet committed money for this, but hopefully it will happen, and we'll see where it goes. Now the click, which the CERN is trying to come up with. So here is the LHC ring, and the click would come up here. This is where CERN is. So for a 380 GeV machine, this is how long the tunnel would be. And to go up to 1.4 TeV, it would have to be this long. And then if it has to be 3 TeV, it has to be this long. Really, really long. And okay, I'll skip these details. I think we don't need them. And these are the main processes. Again, the standard process at the LHC will change, and other processes will become important, including vector boson fusion. And these are some of the kind of cross sections and so on you would have there. And you will also see other kinds of processes which would help you measure the quartic Higgs coupling in detail. Now, I'll again show you how well you can measure the quartic Higgs coupling, but let us not let's look at some of the other things. Let's now move to China. So the Chinese have come up with the idea of building their colliders here and in this place. And it's interesting to know that this is an interesting place because it's close to one of the earlier great things built by the Chinese. So here's the map. So here it is. This is Tangshan, which people may remember was the scene of a great earthquake. Here is Beijing. It's not too far from there, but it's another wonder of the world which is there, which is close by. That's where the Great Wall of China. That's it. And Wang Yufeng is the sort of has been the moving spirit behind these colliders. So this is smaller one is the electron one, and the bigger one is the Hadron Collider they are planning. So here is the sort of layout they will have. Skip the details, but how it compares with the others, with the LEP and this Chinese one, ILC and so on. But here is a slide which I have taken from a talk by Wang Yufang in 2018. So he talks about the latest politics in his language. So science and technology is strongly supported by this government, and it's not difficult to find local support for the science. So this is different from INO, for example. But of course, in China, we know what happens if you protest. So it's not the same as India. Now I'll take this a little ahead. So you'll see the research has been going on full scale. This was published in this year, development of the prototype magnets and so on. And then we come to muon colliders very briefly. Muon colliders, I've shown you that the muon does coupling to the Higgs. So there is a coupling to the Higgs, and you can use it as Higgs factory to create muons, though the coupling is very small. You can still run it in the Higgs mass resonance. That's an effect which allows you to get large numbers of Higgses. It requires a smaller circular collider. Once again, the muon mass is about 2007 times the electron mass, but take it to the 4th power, and then you have much less synchrotron radiation. So time dilation keeps the muons quasi-stable, so that more or less it's stable for all practical purposes. However, the muons decay. They do decay eventually, and when they decay, you get electrons instead of muons. So if you focus it for muons with a particular magnetic field, then that gets because electrons have got mixed up. So a clear solution has not yet been found, and they're easy to produce and so on. I'll leave those details. Then we'll finally come to the idea of laser plasma acceleration. See, what happens, this is a typical collider. These are called RF cavities, and radio frequency, and there's a radio frequency AC connected to them. And every time a charged particle passes through them, it gets an acceleration, which keeps alternating. The maximum field you can put here is about 100 megavolts per meter. If there's a breakdown, there'll be sparks, the whole thing will collapse. Now, what was discovered that in a laser, so in a laser, you could, so this is what happens so the proton always feeds a forward direction. Now, in a laser, a plasma can support electric fields as high as 100 gigavolt per meter, or even a teravolt per meter. Very, very high electric fields. And if a cavity would contain a plasma, the energy imparted can be a few hundred giga electron volts instead of 100 mega electron volts. However, you can't make a container for the plasma. If you could, then you could create a high energy tabletop accelerator. So what people have done, you can of course have a plasma in equilibrium, but these high fields are not there if the plasma is in equilibrium. But if there is a projectile passes through the plasma, and suppose you shoot a bullet through the plasma will oscillate, and then you will see these high fields in the wake of the projectile. So they are called wake field oscillations. And now one of the ideas that don't use a projectile, use a short but powerful laser pulse, which is really a bunch of tightly correlated photons, and use that as a projectile. So use a short but powerful laser pulse, let the lasers go through, and then you send the electrons just behind that. So the wake field will then shoot out these electrons with very high energy. But the timing has to be just right and so on. But this is sort of the picture. The laser pulse creates the wave. And the oscillations where the high fields are there, and the electron bunch is just sent behind that. So it's a very promising technology. It's being vigorously pursued all around the world. It has still to achieve very high energies. I think 4 GeV is the maximum energy they have reached. They reached in 2014, and after that, I'm not sure whether much improvement has happened. Nothing very dramatic. Well, there are other kinds of colliders people have thought of, and they have their good and bad properties. But I've should come to my end of my talk now. Let me talk about the ultimate collider. So what is the ultimate collider? The maximum possible electric field you can have before the vacuum itself breaks down is about 1.32 to 10 to the 12 megavolt per meter. So if you could use such fields, then a linear collider can reach the Planck scale. That's where gravity unifies it with everything else. which is here. That's the mass. So what does the length need to be? You can calculate. It's about 10 to the 7 kilometers. So that would be the ultimate collider, which reaches the Planck scale. It's just about 1/100th of the Earth's distance. Okay, that's a big distance today. But perhaps one day a technologically advanced human race would be able to build such a collider. So then you would have such a huge collider in space like that. And as the Earth rotates, we would see this collider. It would be a space station or a satellite of its own. And perhaps there all the final discoveries of particle physics would happen. This is a dream or science fiction, if you like. But many of these dreams eventually come true. And anyway, so it's time to close. So thank you very much for listening.
Thank you,
Shall I stop?
Professor Raychaudhuri, for your very excellent overview and plans about the future colliders. I feel that with your lucid description, you could reach out to even non-experts like me. I'm sure there are many questions that the audience would like to ask. So I would now request Dr. Parthakonar to conduct the question and answer session.
I'm seeing some of the chat questions will come in the chat box soon. By that time, maybe I'll start with asking something I was thinking for this time when Sreerup was talking about different collider. So this is one very kind of unfamiliar, say decades ago. Now this cosmology has a big impact in our particle physics discovery. Means lots of cosmology experiments now have a very big impact in particle physics. So whether we can expect some of these cosmological experiments also contribute in some big way in our particle physics discovery.
Well, the problem with cosmological experiments is there's an issue of precision in them. First, because anything you get from the cosmos has a very low flux. So we do get precision measurements. We do get some precision. The precision has improved by leaps and bounds, let us say, over the last 30 years. 30 years ago, we used to joke that in cosmological results, the error bars are put in the exponent. But now it's not like that. They're fairly precise. But I don't think the precision will match anywhere near where the colliders go. Also, the cosmological sources, they are not tangible in some sense. I mean, one theory is as good as another. So if you have two different theories, there is no way you can test. It's not in your control. Things are happening somewhere, they have happened somewhere typically and come. They're not in your control. You see what you can see. But here you can control and you can try different experiments, try different options. So there is much more freedom in having. It's just like having a laboratory experiment. In the laboratory, you can do things. With a telescope, you can only see things. So of course, cosmology experiments would be useful, but they will not be enough. That's the point I'm trying to make.
So as you told about this precision machine and as a discovery machine, so there are two sides of that. So at present at LHC found a Higgs. So natural thing is that to go for a Higgs factory, as you have told, for muon collider or Higgs factory. But
yes,
Higgs factory,
or even ILC.
Yes,
or even ILC as a Higgs factory is being thought of. Yes.
Yes, but now how Higgs factory can contribute in the BSM search?
Well, the Higgs, as you know, of course, the Higgs width, the width of the Higgs, the decay width, is far smaller than any precision we can reach till now at the LHC. And therefore, in some sense, if the Higgs has rare decay modes to new particles, perhaps, or through higher order quantum effects, those are not difficult to measure at the LHC. So if you have a Higgs factory with a huge number of Higgses, you may be able to see that. I'll give you the example that at the UA1 and UA2, for example, they had measured the Z but they could not do a precision measurement of the Z-line shape, the way the things the Z decayed into, what was its cross-section into things and so on. But at LEP, it was possible because they produced a huge number of Zs. So it was like having a very high flux. Always in quantum mechanics, your number is the cross-section into the flux. So the flux increases, the number increases. Everyone knows statistics, number increases, the error decreases. Your measure is more and more precise. So this was possible with the Z factory, which LEP was. Now with the LHC, it's sort of general, all multi-purpose machine. But if you have a Higgs factory, you will produce many Higgses, billions of Higgses, and then you would be able to make precise measurements of the Higgs couplings. Now, if the Higgs is the only light particle we have, and that danger is there, then the only way you can see higher particles is by looking at the precise couplings of the Z and seeing if there are quantum effects there which will be different from the standard model. So precision is very important because it may, in a bad scenario, be our only possible handle to higher energy processes. So hence the need for the high precision. Thanks.
Okay, some question came, so I'll read, or you can also see in the chat box. So
let's see. Okay, which accelerator method could address the strong CP problem? Well, I'm afraid I don't know. I don't know whether it can be addressed by, because the strong CP, it has already maybe measured to be a very small value. Very small value, which is already a big, you have a strong CP parameter, which is many orders of magnitude small, and it's 10 to the minus something, 12 or something. Whereas if you just had the QCD, it would be 1. So now this is a problem which is, you don't need an accelerator to worry about. You should worry about it as it is. It's already a big problem. So I can't think of an accelerator which would solve this problem. It has to be solved by some deeper understanding of physics. And so that is the other one you're asking, is it possible to measure the size of an electron? Well, again, the precise size of an electron is 0 because it's a point charge. But the electron has a charge radius which comes from the vacuum particles it's created around it. And of course, as you go to higher and higher energies, you probe more and more. So it's very simple. The higher the energy, the smaller the size to which you can probe. And that is happening. That will happen. So so if you build an accelerator 10 times of the energy, then you have your de Broglie wavelength will be 10 times smaller, so you will be probing it in more detail. So the exact distribution of charge around an electron, you'll be able to measure. Okay, then there is a question. As you stated, there's a higher need for accelerators to get bigger and better. How long will it take till there will be a new discovery that helps us complete the standard model or replace it? You have to go to an astrologer for this. I don't know. I hope it will happen next year. But if it doesn't happen next year, I hope it will happen the year after that. We don't know. Okay. If I knew, then I would not be here. And people would be flocking to me to tell me, ask me what their future is. Then, so I think I should mention the names. The first two questions were by Vijay Sahu, and this last question was from Advait GS, and this one is the name is not this. So
yeah, it is from
Vishal Nag. So he said new techniques which are very powerful. Can you comment on the issue of physical interpretation of the high-end deep learning models? Well, what is the issue? There is no issue. The deep learning models, basically what is deep learning? It just enables you to use the data you have to build a more precise algorithm to look for more data. So the more you have, so of course, see the data itself will not give you a physical interpretation. It will help you to, once you'll have to have a physical interpretation in your mind. You cannot do this out of, cold, as the American would say. There has to be an interpretation in your mind, and then you devise better and better ways to make that accurate. That the machine learning algorithm will do. but it can't tell you how to search. That has to come from your mind. Partha knows much more about this than I do. So if you want to comment on it, Partha, you could do that.
Okay, Vishal is an expert in machine learning, so he is in this. He can unmute and he can tell probably.
Yes.
Oh, sorry, he don't have mic. So probably what he is mentioning that physical interpretation means when you are looking at the from the deep learning perspective, the same data we are having accessing this from Large Hadron Collider or any of this collider. So there are lots of uncertainty. So basically, you are interpreting the data from a black box, basically. So physical intuition probably will be less. So that kind of uncertainty is how to take care. That would be the major challenge. So that is probably he mentioned here.
Yes, but at some time you have to make a contact with the physical model. And that is where the deep learning will not tell you. It will just give you the accurate numbers. That's all.
Yes.
Whereas how to compare it and how to understand it will, as I said, will have to come from your mind. Okay. Another question. Low energy experience have already put an upper bound to stop CP violation, which should be complemented by direct measurement in some ways. Yeah, you could do the upper bound could improve, but these are generally not done. You see, a high energy collider will not help you with this because you are looking for QCD effects. You're looking for strong interactions, and as you know, the QCD coupling is large at low energies. So if you want to see large, then these typical colliders, low energy colliders or colliders of a different kind, like the Brookhaven Rick or something, these are the ones where you would like to see that kind of effect in strong interactions. When you go to very high energies, the strong interactions actually become weaker and weaker because of asymptotic field. And the result is that those are not the right place to look for. If you want to understand more about strong CP violation, look at low energy machines, look at fixed target experiments. Those are the ones to look for with high luminosities. Okay, any other?
Okay, I don't. Yes. Tanmoy.
Yeah, here's a comment. So you see, these are fixed target experiments.
Yes, it is comment.
Yeah.
Okay, because of the mathematical expression, so 10 to the power minus 10.
Yeah.
So any more question from the WebEx? I think some of the theoretical physics members are also available here. No, I don't see any more question.
Hello, sir. So can I
Yes.
ask?
Yes, go ahead.
First of all, this is a nice talk. Then I want to ask this in FCC, that is Future Circular Collider, as this is a very high energy machine, so QCD correction will be very less important, right?
Sorry, what will be
QCD,
very less?
QCD corrections will be very less important.
Yes.
Yes.
Well,
Then,
not. Yes, go ahead.
okay, then those type of, like if these some models, some Feynman diagram that is possible only through loop-induced process, then those channels can we search?
What you are asking is that the noise due to QCD in general and QCD corrections will be less at such a machine. There's no question about that. But not so small as to ignore. Because QCD is at the LHC, for example, it's many times stronger than the electroweak couplings. It will go down, but it will certainly go down. But it will not go down to an extent that it becomes negligible compared to electroweak. For that, you'll have to take your energy many, many times higher. It doesn't fall that fast.
But in that case,
So-
but in that high energy machine, so FCC, so electric correction maybe is great advantage.
Electroweak corrections will roughly be at the, yes, the electroweak corrections are the ones which will carry loop effects. But the electroweak correction won't change all that much. That's because the electroweak running is much slower than the QCD running. QCD running runs much faster. So let us say QCD may fall to 1/3 or 1/4 or whatever it is. The electroweak coupling will change only, let's say, by 10% or 15%. So that's the kind of advantage you will get. Yes, it is true that the electroweak, the QCD coupling, QCD corrections, QCD noise, all these will fall. That's true. But the electroweak one will not increase too much, just the relative change will be more. Certainly it will help. It will help, but it's not a clincher.
Okay, sir.
Okay.
Okay,
Now Satyajit is writing, I heard LHC energy is going to 13.8 TeV in the next run. And next question is, what stops it to reach 14 TeV?
is it only budget or are there some technical issues as well? Well, really, I don't know the answer to this. You'll have to ask somebody who is involved in the accelerator building part. Since I'm a theorist, I don't have access to that kind of information. If they tell me that it's going to be 13.8 TeV, I accept it's 13.8 TeV. I'm in some sense the wrong person to ask. What is the way for the upcoming coalition to reduce the uncertainty in hadronic channels compared with the present collider results? Up to what order it can improve? I think I just answered that. Yes.
It is similar question.
Yes. Are there any more in the YouTube perhaps?
No, YouTube was pasted here. So few
Okay.
thanks, and Vijaya, thanks you for his answering.
Thanks for your questions.
Yes, I think that's all. Yes, thank you. I don't think answer here. So thank you for wonderful talk and insightful discussion. So I think hand over to Nandita.
Yeah, thanks, Partho, for conducting the question and answer session smoothly. And thanks also to Professor Raychaudhuri for taking all the questions and patiently answering them. I would now like to request Dr. Manesh Samal to give the vote of thanks and conclude the session. Manesh, please.
Thank you, Professor Nandita. Friends, it is an honor to propose vote of thanks to all who have helped us in making today's Vyakhyaan possible. First of all, I, on behalf of PRL, would like to thank today's speaker, Professor Raychaudhuri, for accepting our invitation and agreeing to share his knowledge with us. Professor Raychaudhuri, we are truly thankful to you for enlightening us on history of various colliders, their role in discovering of patterns to Higgs bosons, and you also discusses limitation of standard models and how future colliders and unbiased search techniques may help to understand physics beyond standard model and may unravel many new physics. It was really encouraging and inspiring. Once again, I thank you for your time and delivering such a wonderful Vyakhyaan. I also thank Professor Anil Bharadwaj, Director of PRL, Professor Pallam Raju, Dean PRL, and all the Vyakhyaan committee members for their continuous efforts to make this Vyakhyaan series keep going. Finally, on behalf of PRL, I extend our special thanks to all our participants and panelists who have joined us through WebEx and YouTube platforms. Thank you all for your time. With this, we come to the very end of today's chapter of PRL ka Amrut Vyakhyaan. See you next week, another yet interesting Vyakhyaan. Till then, goodbye to you all. Have a great evening.
Thank you. Goodbye.